Okay, let's look at this question. For 150, delete node in a BST. The question itself is easy to understand. We got a BST and a key, which is the input, and we need to delete the node with the given key in the BST. Return the root and reference. Basically, there are two typical stages. First is to search for a root node to remove. The second is to find that code and find the node and delete the node as needed. Let's look at the ideas to solve this problem. And the key idea here is to consider the node type, different types of node. And for example, this is our input binary search tree. And so the question is, how many different types of nodes if we want to remove? So typically in this question, we consider three typical cases. First one is the leaf node. For example, if we want to delete the 7, this is the leaf node. And the second case is that the node with one child. For example, if we want to delete this, it has one child, 7, and this is this type. And the third case is that we want to delete the node with 2 children. For example, we want to delete this node. It has, or delete this node. The common property of those two nodes is that they have two left side and right side subtrees, I mean the child. And then let's start to consider how to solve different cases here for the leaf node and one child and 2 children. Let's start with our original example, or we can simplify this, just consider the leaf node. Let's say the tree is 5, 3, 6, which is really simple. And if we consider if we want to remove this one, how will we update the tree? So we just delete it and then set the right side of this pointer as null. So the result is something like this. Oh, no. The result is this one. And here is a null. And similarly for the left side tree. And I think the idea is really simple here. Let's look at another case, such as the tree with one child, like this one. Then in this case, if we want to remove, let's say, this node, we want to remove this node like 6. And how will we modify this tree? We can delete this node and then set the right side of its parent node to the children of the node we targeted. So the results will become 5, 3, 7, like this. And if we don't have 7 here, if this one currently for this example, this one child is at the left side of this subtree. If it is at the right side, like this, such as this one, use different color, such as 5, 3. And in this case, if we want to delete 7, what should we do? We want to delete 7 and it has a one child 6. And similarly, we still need to recite the right side of this node to this node. This node is the left children of the node we targeted, so the tree becomes 5, 3, and 6. So the conclusion is that no matter this one child is at the left side of at the right side of the left side, we just need to cite the right pointer of this parent node to it, and the result is also similar if it is at the left side. For example, in this case, if there is 2 and we want to remove 3, we just need to recite the left pointer of the 5 to this number 2. Let's look at another case. The most general, the complicated case. 5, 3, 6, 4, 2, 4. In this case, if the k equals to let's say 3, and we want to remove this, first we find this position, and then we want to remove it. What should we do? The idea is that there are 2 solutions here. First is to find the maximum value of left side, or find the minimum value of right side, right subtree. Why we need to do that? Because essentially, if we go through this tree by in order traverse, like 2, 3, 4, 2, 3, 4, 5, and 6, 7, it's an increasing order. If we remove this point, we just need to find the maximum value before this node and put this maximum value here. So in that case, this node will become, if after we delete this position will become 2, and the original node with the value of 2 will also be removed. So in that case, we find the target, and then find the maximum value or minimum value, maximum value of left subtree, or minimum value of the right subtree. We can choose one for implementation. And thirdly, we replace the current node. Replace current node. And finally, we also need to delete this maximum value or minimum value. And this is a most general case. So ideally, we can consider all of those situations, but I mean, it is a little bit hard to consider everything clearly at the first time. And for myself, basically, when I first try to solve this issue, I always neglect particular situations. So the good thing is that before the real implementation, try to consider something like this. What is the all the types for this node, and what is our principles to classify these situations? If we have those ideas in mind, we can solve this issue in an efficient, solve this problem in an efficient way. And this is how we solve this problem and how we consider it. Let's look at the code and to implement it step by step. Okay, let's start with the code. And firstly, we need to define a helper function. And why we need to do that? Because in the C++, if we want to remove a node, we need to record its, we need to memory its the parent node of the current node. So let's define this helper function, and it will use the same parameter, and the extra one is the parent. Okay, and then let's start with discussing typical scenarios. First is that the root edge case, which means root is non-pointer, and then we need to find particular node. I mean the node that we targeted, like, so we need to find targeted node. If we find that node, we then start to look at particular cases, like case 1, the node is the leaf node. Case 2, there is one child. And case 3, and there are 2 children. Okay, for this case, just check the root value. Return. Then start to find the targeted node according to the property of the binary tree. We just need to explore, need to compare the node value. For example, if the key is less than current node value, we just check the left tree. And same, and use same parameters. And the parent node is the root value here. Another case, if the key value is larger than current value, we check the right side, right subtree. And for other case, if the key value equals to the root value here, we find that node, and we need to consider these three cases. For the first cases, if it is a leaf node, which means the right child and left child equals to non-pointer. And if there is one child, we will do things here later. And if there is one child, one of them is non-pointer. And this case, this is case 1, case 2. And for other case, it is case 3, which means there are 2 children. So let's look at the first case. Let's open the description here. For example, in this case, as we discussed just now, we just need to remove the leaf node directly. And firstly, we need to adjust if parent node is non-pointer. For example, we may get the input like this. So in that case, there is only one node, and we just need to delete the current root directly and return a non-pointer. So the parent node of this case is non-pointer. And for other cases, we need to adjust if this node is at the left side or the right side of the parent node. For example, in this case, it is at the right side, and we just need to remove it and cite this left pointer of the 6 as non-pointer. If value is larger than parent value, it is at the left side or child, and parent right equals to non-pointer. And for other case, parent root left equals to non-pointer. Then we delete the root, and those are all steps for the case 1. For the case 2, if there is one child, like this case, if we want to delete the 6, we just need to cite the right pointer of the 5 as the 7, as we discussed it just now. Similarly, we need to decide if the parent node is non-pointer. If the parent node is a pointer, it is a non-pointer, such as, for example, the input tree is only just this subtree, and we just need to return the left side or the right side directly. If left not equals to, if root left exists, we just return root left. Otherwise, else we return, because we have one. In this case, there is definitely one child, so we either return the left or right. Then delete root. For other case, if the parent node is non-pointer, it exists, and we need to decide if the current node is at the left side or the right side of the subtree. For example, in this case, the parent node is 5. If we want to delete 6, the parent node is 5, and it is at the right side of the this parent node, and we set the right pointer of the parent node and let it point to the 7 directly. So if the root value is larger than the parent, so it is at the current value is at the right side of the parent value. We recite the right pointer, and if the root right exists, parent right equals to the root right. If the root left exists, parent value right equals to root left. So, for example, in this case, the root right exists. So it has a 7. So we set the pointer as the 7, right pointer of the 5 as 7. If we have so in other case, if we have a node here such as 5.5, we set the right pointer of this 5 to this node if it exists. Then after these operations, we delete the current node. And then we do similar things at the left side. If root right exists, parent left equals to root right. And similarly, if root left exists, parent left equals to root left. And then we delete root. So be careful about this part and to make sure we do not miss some details. And for the last case, case 3, we have 2 children. And in that case, as we discussed it just now, we need to return the maximum value of the left subtree of the, the maximum value of the left subtree or the minimum value of the right subtree, and replace the current node with this value. For example, if we want to delete 5, in this case, we just need to put 4 here. So we need a function tree node, get this left maximum node. Let's say we call that find max right tree, and we will implement this function later. I think we get this value and we check the left maximum. Yeah, we set the left maximum value as its value, and then Oh, here is some important or interesting part. We need to remove this pointer from the left subtree, and we can reuse these existing functions to do that. I think it's a really smart point for this question. You could see here, we call this function, the root of this function is this subtree, and the key value is this one, and the parent value is current root. By doing this, we can successfully remove the left subtree, remove the maximum value from the left subtree, assume the function is right, and the code looks really simple in this case. And at last, we just replace the current value by this maximum value. And after doing this, and we can return the current node, return the root. Yeah. Make sure, yeah, it's in this else part. And let's implement this function, find max. So we just need to return the helper with k and non-pointer for the initial case and implement this find max function. Find max function. Yeah, it receives this tree nodes. We just need to find the rightmost. We check the right side of the subtree and find the maximum value here. Use a while loop here. While root right not equals to non-pointer root equals to root right, and then return this root. And yeah, let's say if it works, we can go through all code quickly, and we use this helper function, check the edge case, and find the targeted value to say if it is a one leaf node to a one child node and two children. For the one for the leaf node, just delete the node directly and set the right and left pointer of the parent node. For the one child case, check the parent firstly and then recite the left or right of the parent node as a subtree of the current node, as a subnode of the current node. For two children case, find the maximum value of the subtree and replace its value, replace the value of the current root. Let's see if it works. Oh, some typo here. Yeah, it works as expected. Okay, let's quickly summarize this question. And there are several tips. First is we need to have an idea about the types of node. In this example, we classify it as leaf node and the node with one child and the two children. This is a typical form of a node classification. In other problems, we might use different types of node classification. But anyway, if you don't classify the node into different cases, you may confused a lot during the programming, and by this way, it will make the whole framework more clearly. Second is the edge cases. For example, during the implementation, we need to consider what if the node is a non-pointer or the parent node is non-pointer and some edge cases, and we need to handle it carefully. The third case that the in-order traverse of the binary tree is also an increasing sequence. So if we know this fact, we can utilize this fact to solve some problems more efficiently. For example, in this case, we search the minimum value of the left subtree and the maximum value of the right subtree. And I think this is the idea we can acquire from this question. Thanks for watching and see you next time.